Each celestial body within the vast architecture of our solar system possesses a unique intrinsic character, a signature written in stone, gas, and ice. Some of these worlds appear to us as monuments frozen in the corridor of eternity, such as the desolate, wind-swept oxidation of Mars, or the distant, nitrogen ice-encrusted silence of Pluto. Others are veiled mysteries, shrouded in dense, opaque envelopes of gas like the crushing, acidic atmosphere of Venus or the hydrocarbon haze of Saturn's moon, Titan. However, situated in the immediate, perilous vicinity of the gas giant Jupiter, there exists a world that defies the archetypal stillness of the vacuum. It is a world where the planetary interior shudders with violent convulsions, where hundreds of roiling calderas launch ballistic assaults against the void of space, expelling matter in gigantic plumes. It is a world where the horizon is dominated by the oppressive bulk of its parent planet, which frequently eclipses the distant, diminished sun, plunging the landscape into sudden darkness. This is a landscape painted not in the subtle grays of the moon or the rusty reds of Mars, but in a chaotic, vivid palette of millions of yellow, orange, red, and black hues. This is Io, the innermost of the Galilean moons of Jupiter, a celestial body that is at once dangerous, furious, and scientifically profound. To understand the magnitude of Io's existence, we must first cast our minds back more than 4 centuries, to the dawn of telescopic astronomy. In the year 1610, the Italian polymath Galileo Galilei turned a primitive optical instrument, a small refracting telescope by modern standards, toward the bright wanderer known as Jupiter. In doing so, he facilitated one of the greatest paradigm shifts in the history of human thought. Beside the gas giant, he resolved 4 points of light, initially believing them to be background stars. Night after night, however, their positions shifted, oscillating around the planet. These were not fixed stars, but satellites, a realization that shattered the Aristotelian geocentric model which posited that all celestial motion centered upon the Earth. One of these objects was Ganymede, a moon of such immense proportions that it is now recognized as the largest satellite in the entire solar system, exceeding even the planet Mercury in diameter. 2 others, Europa and Callisto, have since been revealed by modern spectroscopy and gravity science to hold vast subsurface oceans, making them premier candidates in the astrobiological search for extraterrestrial life. The 4th object, the one orbiting closest to the chaotic cloud tops of the gas giant, was eventually named Io. For centuries following its discovery, Io remained merely a point of light, its nature obscured by the limitations of terrestrial optics. Its composition and internal machinery were matters of speculation, hidden behind the resolution limit. It was not until the dawn of the space age and the advent of robotic exploration that the true nature of this world began to materialize. Today, we recognize Io as the 4th largest satellite in the solar system, possessing a physical stature that commands respect. Its mean radius is approximately 1,821 kilometers, and its mass is calculated at roughly 8.9 times 10 to the power of 22 kilograms. To provide a contextual framework for these figures, one might compare Io to Earth's own moon. In terms of dimensions, the 2 bodies are remarkably similar, almost identical in radius. However, when one examines their mass, a striking divergence appears. Io is approximately 21% more massive than our moon. This discrepancy in mass, despite similar volume, leads to a critical deduction regarding density. Io possesses the highest density of any moon in the solar system, with a mean density of approximately 3.5 grams per cubic centimeter. This density value is not merely a number. It is a diagnostic clue to the Moon's composition. It suggests a bulk makeup significantly different from the ice-rich worlds of the outer solar system. A density of 3.5 grams per cubic centimeter correlates with silicate rock and iron, implying that Io is composed primarily of non-metallic minerals and heavy metals, much like the terrestrial planets, Mercury, Venus, Earth, and Mars. Unlike its neighbor Europa, or the distant Ganymede and Callisto, which contain substantial fractions of water ice and volatiles, Io is desiccated. It is a rock-metal world. To understand why Io is so anomalously dense and dry, we must look into the history of the Jovian system's formation, but more immediately, we must peer deep into the Moon's stratified interior. Current geophysical models, derived from gravity data and moment of inertia calculations, suggest that Io is a differentiated body. This means its internal components have separated by density. At the very center lies a core, relatively compact, composed primarily of iron and iron sulfide. This metallic heart is estimated to account for approximately 20% of the satellite's total mass. The radius of this core is a subject of ongoing scientific debate, with estimates ranging widely from 350 to 900 kilometers, depending on the specific mixture of sulfur and iron assumed. Thermodynamic calculations regarding this core present an interesting constraint. The internal heat generation, while immense, is likely insufficient to maintain the entire core in a molten state at the temperatures required for pure iron convection. This hypothesis aligns with observational data. Io lacks an intrinsic, self-generated magnetic field. If the core were vigorously convecting molten iron, we would expect a dynamo effect similar to Earth's. Its absence suggests a core that is either solid or stagnant. Surrounding this dense, metallic core is a massive silicate mantle. This rocky envelope constitutes the majority of the Moon's volume. It is believed to be composed largely of magnesium-rich minerals, specifically forsterite, the magnesium end member of the olivine solid solution series. This is a common mineral in the upper mantles of terrestrial planets, known for its high melting point and ultramafic character. The state of this mantle is where Io diverges radically from the Moon or Mars. Gravity measurements and the Moon's response to tidal forces indicate that the mantle is not entirely solid. There is strong evidence for a global subsurface layer of partial melt, essentially a magma ocean, encircling the Moon beneath its crust. This layer is estimated to be at least 50 kilometers thick. The temperature within this molten or semi-molten region is inferred to be extraordinarily high, approximately 1,600 Kelvin, or roughly 1,326 degrees Celsius. Such temperatures are sufficient to melt ultramafic rocks, producing lavas with very low viscosity. Beneath this asthenospheric layer of melt, the deeper mantle likely remains solid due to the immense overburden pressure. Even though the temperatures remain high, the crushing weight of the rock above forces the mineral lattice to remain in a solid phase, preventing melting. Capping this infernal interior is the lithosphere, the rigid outer shell of the Moon. Estimates for the thickness of Io's lithosphere range from 12 to 40 kilometers. Unlike Earth, where the lithosphere is broken into mobile tectonic plates that drift and collide, Io's lithosphere operates under a different regime. It is subjected to constant, immense stress, not from drifting plates, but from vertical burial and tidal flexing. It is not a monolithic, unbroken eggshell. Rather, It is fractured and faulted, pierced by conduits that allow the ascent of magma from the mantle below. Spectroscopic analysis of the surface reveals a distinct lack of the materials common to other outer solar system bodies. There is virtually no water, no ice, no frozen carbon dioxide or methane. The volatiles have been driven off. Instead, the surface is dominated by basalts, volcanic silicate rocks, and extensive deposits of sulfur and sulfur dioxide. This composition explains the high density and the specific geological behaviors we observe. Our understanding of this complex world was revolutionized in the 20th century, specifically during the 1970s. Prior to this era, our view was limited to the blur of ground-based telescopes. The arrival of the Pioneer 10 and 11 probes provided the first close-up glimpses, but it was the Voyager program that fundamentally altered planetary science. When the Voyager 1 spacecraft flew past Jupiter in March 1979, it returned images that baffled the scientific community. The surface of Io looked nothing like the cratered, dead surfaces of the Moon, Mercury, or Mars. It was devoid of impact craters. Instead, it was mottled, colorful, and geologically young. The breakthrough came when navigation engineer Linda Morabito noticed a peculiar crescent-shaped anomaly on the limb of the Moon in one of the images. This was not a cloud or a sensor artifact. It was a plume. It was a fountain of gas and dust, rising nearly 300 kilometers above the surface. This observation confirmed that Io was volcanically active. It was the first time active volcanism had ever been detected on a world other than Earth. It shattered the prevailing notion that small celestial bodies must be geologically dead due to rapid heat loss. The energy source driving this activity was not residual heat from formation, nor radioactive decay, but something else entirely: gravitational tides. Subsequent analysis revealed that Io hosts approximately 400 active volcanic centers. While this number is numerically smaller than the total count of volcanoes on Earth, one must consider the surface area. Io is significantly smaller than Earth. When normalized for surface area, Io produces roughly 100 times more lava than Earth. It is, unequivocally, the most volcanically active body in the solar system. The resurfacing rate is so high that impact craters are erased almost as soon as they form. The surface we see is constantly being buried under new layers of lava and pyroclastic fallout. By 2012, using the accumulated data from Voyager, the Galileo orbiter, and flybys from the Cassini and New Horizons missions, scientists were able to compile a complete, global geological map of Io. This map is a cartographic masterpiece of chaos. It details distinct morphological provinces, vast plains coated in sulfur dioxide frost, towering mountain ranges that defy gravity, intricate lava flow fields, and the ubiquitous Pattery, the volcanic depressions that serve as the mouths of the underworld. One of the most visually arresting features identified on this map, and indeed one of the most iconic structures in the solar system, is the feature known as Peel. Located in the heterogeneous terrain of the trailing hemisphere, Peel is surrounded by a gigantic, distinctive red-orange ring. This ring is not a solid structure, but a deposit. It is an annulus of fallout, a footprint left by the volcanic plume. The Peel plume is a persistent, towering geyser of sulfur and sulfur dioxide gas, along with fine dust particles, rising 300 kilometers into space. The material is ejected at supersonic speeds. Because Io has a very tenuous atmosphere and low gravity, the plume does not billow like a cloud on Earth. Instead, it follows a perfect ballistic trajectory, creating a vast umbrella shape. As the sulfur gas rises, expands, and cools, it condenses into tiny frozen particles. These particles then rain down back to the surface, painting the ground. The ring itself stretches more than 1,000 kilometers in diameter. To put this in perspective, the area covered by the fallout of this single volcano is comparable to the land area of a large country like Egypt or the combined area of France and Germany. It is a depositional feature of continental scale. The coloration of the peel ring, that deep, rusty orange and red, provides a lesson in the chemistry of sulfur. Elemental sulfur is a polymorph. Its color changes depending on its molecular structure and temperature. Pure sulfur is yellow at room temperature. However, when it is heated and melted, the sulfur rings break and polymerize into long chains, turning the liquid red, then dark brown or black as it gets hotter. When these allotropes are quenched, cooled rapidly, they can retain these reddish hues. Furthermore, radiation from Jupiter's harsh magnetic environment can alter the crystal structure of the sulfur, darkening it and shifting it toward red. The center of the peel feature is a dark accumulation of hot lava, a volcanic crater known as a patera. Infrared imagery confirms that this is an active lava lake, radiating intense heat, constantly replenishing the plume that paints the surrounding landscape. This volcanic activity is inextricably linked to Io's atmosphere. Unlike the substantial atmospheres of Earth or Titan, Io's gaseous envelope is extremely thin, often described as an exosphere. The surface pressure is roughly 1/1000th of Earth's atmospheric pressure. The primary constituent is sulfur dioxide, with trace amounts of sulfur monoxide, sodium chloride, and atomic oxygen and sulfur. The dynamics of this atmosphere are governed by a delicate balance between sublimation and volcanic injection. During the Ionian day, sunlight strikes the surface, heating the frozen sulfur dioxide frost. The frost sublimes, transitioning directly from solid to gas, thickening the atmosphere. At the same time, volcanoes pump tons of gas directly into the sky. However, a dramatic phenomenon occurs when Io passes into the shadow of Jupiter. During this eclipse, the temperature plummets. The tenuous sulfur dioxide atmosphere cannot sustain itself in the cold. It collapses. The gas condenses and frosts out onto the surface, leaving the moon in a near vacuum. When Io re-emerges into the sunlight, the frost sublimates again, reinflating the atmosphere. This collapsing atmosphere model was a theoretical prediction that has been confirmed by observation. Furthermore, this atmosphere is not isolated. It interacts violently with Jupiter's magnetosphere. Jupiter possesses the strongest magnetic field of any planet. This field rotates rapidly, sweeping past Io. It strips tons of material from Io's atmosphere every second, ions of sulfur and oxygen. This material forms a donut-shaped cloud around Jupiter called the Io plasma torus. As the magnetic field lines sweep through Io's ionosphere, they generate massive electrical currents, millions of amperes strong, which flow between the moon and the planet's poles. This interaction creates auroras on Io, glowing curtains of light in the tenuous gas, and also contributes to the massive Jovian auroras on the giant planet itself. Moving away from the volcanic plains, the geological map reveals another dominant landform: mountains. One might expect the mountains of Io to be volcanoes, similar to Mount Fuji or Kilimanjaro. However, the majority of Io's high peaks are tectonic, not volcanic. They are blocks of crust that have been thrust upward. The Barsal Montes is a prime example of this non-volcanic topography. Located near the South Pole, this mountain range is a testament to the immense stresses within Eo's lithosphere. The highest peak in the Barsal array reaches an elevation of approximately 17 to 18 kilometers relative to the surrounding plains. For comparison, Mount Everest stands 8.8 kilometers above sea level. The Barsal Montes are twice as tall as Earth's highest peak. The formation mechanism for these mountains is driven by the rapid burial of the crust. As volcanoes erupt, they lay down layer upon layer of lava. This relentless deposition pushes the older crust downward. As the crust sinks, it moves into a sphere of smaller circumference. This geometric constraint forces the crust to compress. To accommodate this compression, the rigid lithosphere fractures and thrusts blocks of rock upward, creating towering, tilted massives. These mountains are incredibly steep and rugged. Due to the lack of wind or water erosion, they degrade primarily through mass wasting, landslides. Giant scarps often collapse, sending debris cascading down to the sulfur-rich plains below. Let us now turn our attention to one of the most formidable volcanic features on the satellite, Loki Patera. Named after the Norse god of trickery and fire, this feature is the largest volcanic depression on Io, spanning roughly 200 kilometers in diameter. It is not a mountain peak but a vast sink, a caldera filled with a sea of molten rock. Loki Patera is fascinating because of its periodic behavior. It is a lava lake, but unlike the small, churning lava lakes on Earth, Loki is immense. The surface of the lake cools to form a dark, solidified crust. However, this crust is denser than the molten magma beneath it. Over time, the crust thickens and becomes unstable. Eventually, a section of the crust sinks, or founders. This initiates a catastrophic, overturning wave. The sinking crust exposes the incandescent magma beneath, causing a massive spike in thermal emission visible to telescopes millions of kilometers away. This wave of resurfacing propagates across the lake over a period of weeks or months, slowly replacing the cool crust with fresh lava before the cycle begins anew. It is a rhythmic, slow-motion cataclysm that releases more heat than all of Earth's active volcanoes combined. Further exploring the map, we encounter the region known as Media Regio. This area exemplifies the complex interplay of different terrain types on Io. It is a transition zone where the smooth, sulfur-coated plains meet the rugged, fractured highlands. The coloration here shifts from the bright white and yellow of sulfur dioxide frost to the darker browns and reds of silicate magmas and sulfur polymers. It is a chaotic interface, demonstrating that Io is not a uniform world, but a mosaic of geological provinces, each with its own history of deposition and deformation. Among the active centers, the volcano Amirani deserves specific mention. Located in the leading hemisphere, Amirani is the source of the longest active lava flow known in the entire solar system. The flow field emanating from this center extends for approximately 300 kilometers. The dynamics of the Amirani flow offer insight into the rheology of Ionian lava. To flow for 300 kilometers without freezing requires a specific set of conditions. The eruption rate must be high, and the lava must be insulated. It is likely that these flows travel through lava tubes, insulated tunnels of rock that prevent heat loss to the cold vacuum, or that they are sheet flows of very low viscosity, ultramafic lava, spreading rapidly over the surface. The interaction between the hot lava and the volatile sulfur frost on the ground creates secondary steam explosions, pitting the surface and creating a localized, chaotic atmosphere around the advancing flow front. We must now address the fundamental question: what drives this hellish activity? Why is Io a world of fire while its neighbor, the moon, is a cold, dead rock? The answer lies in the celestial mechanics of the Jovian system, specifically a phenomenon known as orbital resonance. Io is not alone in its dance around Jupiter. It is locked in a specific rhythmic relationship with Europa and Ganymede. For every 4 orbits Io completes around Jupiter, Europa completes exactly 2, and Ganymede completes exactly 1. This 1, 2, 4 resonance is known as the Laplace resonance. The gravitational interaction between these moons prevents Io's orbit from circularizing. Left alone, tidal forces would eventually make Io's orbit a perfect circle. However, the tug of Europa and Ganymede keeps Io's orbit slightly elliptical or eccentric. This eccentricity is the key. Because the orbit is an ellipse, Io's distance from Jupiter changes throughout its orbit. It moves closer to the giant planet. As Io moves closer, the immense gravity of Jupiter stretches the moon into a prolate spheroid, like an American football pointing toward the planet. As it moves further away, the gravitational pull weakens, and the moon springs back toward a more spherical shape. This happens every 42.5 hours, the length of Io's orbit. The solid ground of Io rises and falls by as much as 100 meters during this cycle. This is not a tide of water, it is a tide of solid rock. This constant, rhythmic squeezing and releasing creates friction deep within the moon's interior. Just as bending a metal wire back and forth generates heat, the tidal flexing of Io's mantle generates massive amounts of thermal energy. This process, called tidal dissipation, generates approximately 100 trillion watts of power. This heat melts the mantle, drives the plumes, powers the overturning lava lakes, and builds the mountains. Io is essentially a heat engine powered by gravity. Another manifestation of this power is seen in the Tvashtar-Patari region, a chain of volcanic craters located in the northern hemisphere near the pole. This region gained fame during the flyby of the New Horizons spacecraft en route to Pluto. The probe captured a sequence of images showing a massive plume from Tvashtar, rising 330 kilometers high. The structure of the plume was intricate, resembling a curtain of fire or a grand fountain. The Tvashtar eruption provided critical data on the temperature of the lavas. Detailed measurements suggest the lava temperature can exceed 1,600 Kelvin. This extreme heat supports the hypothesis that the lavas are ultramafic, rich in magnesium and iron, similar to the lavas that erupted on Earth billions of years ago during the Archean Eon. In this sense, observing Tvashtar is like looking through a window into Earth's primordial past. Most recently, the Juno mission, primarily designed to study Jupiter, has provided new perspectives on Io. Unlike previous equatorial orbiters, Juno orbits Jupiter in a polar trajectory. This has allowed the spacecraft to peer down onto Io's poles, regions that were poorly mapped by Voyager and Galileo. Juno's Jovian infrared auroral mapper has captured stunning heat maps of the satellite. These images reveal that the volcanoes are not limited to the equatorial regions, but are distributed all the way to the poles. The infrared data glows with the light of hundreds of hot spots, shining against the cold background of space. Juno has observed polar cyclones of energy, interactions between the volcanic output and the polar magnetic field lines of Jupiter. These observations continue to refine our models of how the moon's internal heat is dissipated and how its atmosphere behaves in the extreme polar environments. In conclusion, Io stands as a testament to the dynamic and violent potential of the cosmos. It is a moon that, by all rights of size and location, could have been a cratered, frozen wasteland. Instead, due to the elegant but brutal mechanics of orbital resonance, it is the most geologically vibrant world we have ever encountered. From the sulfur-choked skies to the heaving magma oceans deep below, from the towering non-volcanic peaks of Barsol to the shifting lava lakes of Loki, Io challenges our understanding of planetary evolution. It serves as a natural laboratory for volcanology, geophysics, and atmospheric science, offering a glimpse into processes that shape worlds far beyond our own solar neighborhood. As we continue to study this moon, analyzing the data from past missions and looking forward to future observations, Io remains a burning beacon in the cold dark, a chaotic, beautiful, and terrifying world that refuses to be ignored.